Lecture 1 covers sections 1.1 through 1.6 and section 3.13. For us to begin this course, we are going to define the following scheme within our notes. Bold words are going to be that of definitions. Italic words or letters represent variables. Underlined words or phrases represent a law, theorem, and/or hypothesis. Bracketed symbols are units. And blue words or phrases, except in the summary slides at the end of the lecture, are hyperlinks. I suggest you click them and read the articles. Each section has a number and title displayed in our right navigation pane, which follows our text, and they are hyperlinked within the PDF. Lastly, important equations will be boxed. Now, each lecture will comprise of a title slide that lists our sections covered from the text. Following our title slide are the student learning objectives, which list the key concepts covered in the lecture. After our learning objectives, conceptual material is presented with appropriate examples. At the end of each lecture, a summary slide of the student learning objectives is presented. And lastly, a list of suggested problems from the text covering the material presented within the lecture is given. Now, today's lecture covers the preliminaries of thermodynamics. At the end of today's lecture, you should be able to understand what comprises a system. You should also be able to construct a control volume through prescribing a control surface, and you should determine whether or not our control volume is open or closed, or whether it's a control mass or isolated system. You should also be able to differentiate between a macroscopic and microscopic point of view. You should be able to understand and identify phases, states, and properties. You should be able to differentiate between intensive and extensive properties. You should be able to identify three common processes and how they relate to cycles. You should be able to calculate density and specific volume. And lastly, you should be able to understand the concept of conservation of mass. Let us begin. Thermodynamics is a science of energy and entropy, both in terms of the storage and conversion of. As engineers, we are interested in converting thermal energy, that is heat, into mechanical energy, most often kinetic energy, either in the form of translational or rotational. And we want to minimize the penalty for these conversion processes, i.e. entropy production, such that we can develop cycles to do things, such as internal combustion engines. Now, thermodynamics dictates every possible action within our universe, and it's governed by four laws: the zeroth, first, second, and third laws. In this course, we're going to focus on phase transformations and processes. A process is the act of going from initial state to a final state of thermodynamic equilibrium, and how these processes relate to common engineering devices. Let us begin by talking about control surfaces and volumes. When we're analyzing a system, which can be a single device or a combination of many devices that contain a quantity of matter taken in a macroscopic viewpoint, we need to define our region of interest. To define our region of interest, we construct a control surface, abbreviated CS. A control surface is an imaginary boundary that separates our system from its surroundings. All devices that contain matter within our control surface are known as a control volume, CV. Now let's consider this coal-fired power plant in Orrville, Ohio. Say we're interested in analyzing the cooling tower. How would we draw a control surface to properly encompass our control volume? To do such, we would draw a dashed line around it, and we'd indicate our control surface by the variables CS. Now we have to further differentiate what type of control volume our control surface has traced out. Is our control surface stationary or moving? Well, relative to the Earth, our control surface is stationary. Then we have to make a further distinction, whether or not our system is open or closed. A closed system does not allow mass to cross our control surface, whereas an open system does allow mass to cross our control surface. Based upon the control surface we drew around our cooling tower, we would say our system is open, for we have steam exiting the top of our control surface. Now, there are particular control volumes for which no mass transfer takes place across our control surface, and these are referred to as control masses. A control mass is a closed control volume, and a control mass contains the same amount of matter at all times. If there exists a control mass where no work or heat crosses the control surface, our system is referred to as an isolated system. Therefore, a control surface defines a control volume, in which there may or may not be mass flow into or out of our system. If there is no mass flow into or out of our system, then our control volume is a control mass. Additionally, if no work or heat crosses our control surface, our system is isolated. For us to analyze our system, we have to determine what viewpoint we want to use. We do not want to analyze our system microscopically, as is done in statistical thermodynamics, where we have to consider the contribution of each individual molecule or particle within our system, i.e. its internal, kinetic, and potential energies, all as a probability distribution function. For this is mathematically cumbersome and computationally prohibitive for large-scale systems. We will evaluate our systems from a macroscopic viewpoint. That is, we are going to consider the total time-averaged effects of all the molecules within our system. For the macroscopic viewpoint to be valid, we must obey the continuum assumption. That is, the volume of interest is much larger than the molecular dimensions of our system. That is, the size of our system is greater than the mean free path of the molecules considered within. And in doing such, our volume is treated as homogeneous and continuous. That is, there is not a distribution of properties within our system spatially. Now, we must discuss what working fluids are. In this course, we are going to use water primarily as a working fluid. For it is abundant, cheap, and has the capacity to store large amounts of energy, and can change phase relatively easily at low temperatures. A phase is a quantity of matter that is uniform throughout, i.e. water can be in a solid, liquid, or vapor phase. A solid phase would be ice, a liquid phase would be liquid water, and vapor would obviously be water vapor. Steam, the vapor phase of water, is used to power steam turbines, the backbone of land-based power generation systems. Now, when we talk about phases, we use a phase diagram to describe our substance based upon two independent properties, typically pressure and temperature. The solid, liquid, and vapor phases are regions defined by our phase boundaries, i.e. the red lines on our phase diagram to the right. Multiple phases can exist simultaneously. That is, at points A, B, and C, we can have a solid liquid vapor phase existing simultaneously at point A, a solid liquid phase existing at point B, and a liquid vapor phase existing at point C. We will discuss more about phases and phase diagrams in Lecture 3. However, if we look at the phase diagram for water to the right, we have a few interesting points. Point A is referred to as the triple point, where water can exist in all three phases simultaneously, and this occurs at 0.608 kPa and a temperature of 0.01 degrees centigrade. Water will boil at a pressure of 101.325 kPa and a temperature of 100 degrees centigrade, as indicated by point C. And water will freeze at 101.325 kPa and 0.0 degrees centigrade, as indicated by point B. Point D is the critical point, where the phase is undefined. Now let us look at example 1. Say we're given the phase diagram of water below, and we want to determine which phase the water is existing on based upon our prescribed temperature and pressure values. Say we're given a pressure of 500 kPa and a temperature of 50 degrees centigrade. We see a pressure of 500 kPa lies between 101.325 and 22,063 kPa, and our temperature of 50 degrees centigrade is lying between points B and C. So we can say this point is going to lie within our liquid region. If we have a pressure of 0.01 kPa and a temperature of 200 degrees centigrade, we see 0.01 kPa is below our published value of 0.608 kPa, and we are well past point C, so we're definitively within our vapor phase. And lastly, with a pressure of 25 kPa and a temperature of minus 20 degrees centigrade, we see we are going to be existing in a solid phase.